Hi, this is ET250, lecture 26A. This is going to be a two-part lecture. In this first part, what we want to go over is an Excel document that I created where it visualizes single phase AC power. And so if you look at what's going on, I want you to have this in mind. You have some element where you have the voltage and current defined as such. And notice the current is defined as going into the positive terminal to make sure that all the signs are positive when we compute power. Passive sign convention still holds, but it just makes it easier instead of having to flip a sign. So this is the element I want you to have in your head while we're going through this visualization. Now, in this Excel document, what do we have? On the left here, notice we can enter in the bolded values, AC voltage and current. So you have to specify the amplitude and the of both the voltage and the current, and the phase and the frequency. So notice I've specified 5 volts, 2 amps, 60 hertz, and then I've defined the voltage phase as 10 degrees and minus 30 for the current. So in this specific case, the current is lagging the voltage by 40 degrees, right? And so if we look at this power angle, which is actually defined here. So the power angle, notice I have all the equations written, is theta V minus theta I. I have it computed here as theta V minus theta I. Okay, so this is in degrees. I've made all the appropriate conversions into radians because that's what the Excel likes, but I have it in degrees because degrees at this point are more intuitive to us. Okay. So I have the current and voltage plotted as well as the instantaneous power. And you can see that here down in the bottom. I have a column of time, column of current, column of voltage, and P, right? Where P is just I times V. We have the VP cosine omega t plus theta V for the voltage and the IP cosine of omega t plus theta I for the current. And you can see I'm just plotting all the values. So you can see every single point. And that's what these three plots are, okay? All right, so this is the voltage in orange, I color code it. Here's the current in blue, and here's the instantaneous power in gray. And what do we notice? We notice that the power is oscillating at 2 times the frequency of the voltage or current. We notice that whenever the current or the voltage is 0, we get 0 instantaneous power. In this case, we're getting a little bit of positive, a little bit of negative. And I can now go in here and adjust the voltage and current. So watch this, I can make this maybe 4 volts. And you can see, look at this, the voltage, the orange line drops. So let's put that up back up at 5. I can go in here and change the phase. So let's say we make the phase negative 20 degrees. So let's do that. Okay, let's go with negative 10 degrees and see what happens. Okay, and notice as the current becomes more in phase with the voltage, the instantaneous power starts shifting up higher and higher and higher. If I make it exactly the same, so let's say they're both oscillating at 10 degrees, right? That means that the phase difference is 0, or the power angle is 0. And look at the instantaneous power. It is all positive, right? This would be like this element is behaving like a resistor. Now notice this purple dashed line. This purple dashed line is essentially the average of this gray line, right? And that is actually the real power. And the real power, we are using the equation IRMS, VRMS cosine of theta V minus theta I. And you can see that written here. Okay, so it's B17 times cosine of B19. So what's B17? Well, that is the apparent power, which is V times I over 2. And you might ask, why over 2? Well, remember, it's RMS. So RMS has a factor of root 2 on the downstairs denominator. You take root 2 times root 2, you get regular, just plain vanilla 2. Okay, so that is the average of the instantaneous power, the real power, and that's this capital P here, and you can see it right here. I have written here just so that you remember. Okay, what do I have on the right over here? Now notice on the right, here's an example of a power triangle. Notice the gray line is S just like here, and the angle is theta V minus theta I. So let's look at an example case. So let's say we go back to the original minus 30 degrees. Okay, so the current in this case is lagging the voltage, and we can see the blue current line lagging the voltage in the orange line, right? And the phase difference between the orange and the blue is in fact 40 degrees, which is the same as the angle difference between the gray line and the real axis, okay? So what would happen if I maintain that 40-degree phase difference, but then just rotated the orange and blue all the way over? Well, what would happen is the orange blue would rotate, but the gray would stay as is. So I could do that. I could go extreme. I could say, let's make the phase of the voltage 180, and let's make the phase of the current 140. And notice what we have. The voltage and current rotated, but notice how the complex power did not change, didn't change its magnitude nor direction, right? So that kind of shows you that the complex power angle only cares about the difference between the voltage and current, not the absolute value. Okay, we can do some other examples. Well, what happens if the current is lagging by 90 degrees? Okay, so let's put the voltage at, let's say, 0 degrees and the current at, let's say, minus 90. And now remember, this approximates an inductor. So this was acting like a pure inductor. What would happen? The current would lag the voltage by 90. And you can see that with the blue and orange line. The current's lagging by 90. And look at this on the phasor plot. The current's lagging by 90. Notice the power. The complex power is pointed straight up. It's all complex, no real part. The P part here is 0. And therefore, what's going to happen? Well, what's going to happen is you have no average power transfer. And look at this dashed line. It's 0. Okay. And you can see the average here of the instantaneous is 0, is nearly 0, and the P here is 0. Okay. If I do the same thing, but treat it as a capacitor, I would get a positive 90. And let's look at what we have. Notice the current is now pointed up, the voltage is pointed to the right, and the complex power is pointed down. Again, if we look at the instantaneous power, yes, there's definitely non-zero instantaneous power, but the average is 0. Okay. I hope this is all consistent with what you're thinking. And then we can even rotate the voltage and current. So let's say I have 45 for the voltage and minus 45. Or sorry, not more, minus 45. Yeah, minus 45. That would work, actually. And so this would still be an inductive system, right? The voltage is leading the current by 90 degrees. And look at the complex power and here and the instantaneous power here, okay? So I hope these examples are all consistent with your intuition. Now, the last thing I want to look at is the Q, right? Now, what is Q again? Q is the amplitude of the component of the instantaneous power that bounces back and forth. And remember, the component of the instantaneous power is this P3 guy. So let's look over here. I actually have it all laid out. The instantaneous power you can either compute as just I times V, but in a previous lecture, we also showed that this instantaneous power is the sum of P1 plus P2 plus P3, where P1 plus P2 is the real power plus the real power times this cosine term, and the P3 is the reactive power Q times the sine of these terms, okay? And notice Q, we can see here, is the amplitude of the component that bounces back and forth. Okay, and that's what I've said here. Now I have actually added this to the visualization. You just have to go here, select data, and I'm going to take away the currents and voltages just so that it's a little less busy. And I'm going to put P1 and P3 and the instantaneous power. Okay, this case is kind of boring because everything's in line, but let me make it a little more interesting. Let me make theta V as 0, and let me make theta I, yeah, we'll keep it at minus 45. So let's look at what's going on here. We know the current's lagging the voltage by 45 degrees, and let's carefully look at what's going on. P1 and 2 is this orange line. Notice it is either all positive or it would be all negative, okay? It doesn't oscillate between positive and negative. That's this term right here or this column here. The third component, this Q sine, is going to be this blue line, okay? So notice that blue line is this column here, and the addition of the blue line and the orange line make up this yellow column, which is the total instantaneous power. And look on the chart, notice that the total instantaneous power in yellow is exactly on top of the gray instantaneous power over here, right? And you can see the yellow and gray right on top of each other. So the addition of these two sum to this. Now notice something. The blue line oscillates back and forth. The amplitude of this component of the instantaneous power is Q, the reactive power, 3.536 in this case. And you can kind of see on the chart, it's 3.56. Notice this, if I move this around, let's say I made this minus 20 degrees for the current. Notice we get something that's a little bit more in phase. There's still a non-zero Q. What's the amplitude here? The amplitude is about a little under 2, look, 1.7. The average now bumps up to 4.7, and you can see that on the plot. You can also see that the Q is this length here on the complex triangle, right? And this length here on the horizontal axis, the real axis, is the P, all right? And notice in this case, because the current and voltage are more in phase, the complex power is a little bit flatter. Notice you can see that the P1 and P2 are getting closer and closer to the total power, whereas this part is kind of getting squashed out, right? What else can we do? Well, let's just play with a few things. Let's go and make it a pure resistor. So a pure resistor, everything's in phase, 0, 0. Look at this. Notice the orange line and the yellow line and the gray line are all on top of each other. So the total instantaneous power is the total power, is the all positive or negative power. Notice the bouncing power is squashed to 0, right? Notice the complex power is pointed straight out. Very good. Okay, let's go to the inductor situation. So if I have the inductor situation, let's go put in a minus 90 again, pure inductor. What do we have? Now notice that the orange line here is squashed to 0. However, this light blue bouncing power is exactly matched with the instantaneous power. And the amplitude of the instantaneous power is Q in this case. All right, and you can see that here. Look at this. Q of ours is 5, and this is bang on at 5. And notice no P, and you can see that here. Okay, so I'm hoping you're seeing consistencies between the complex power, the AC time plots, the complex phasor currents and voltage, the AC time plots, and all the equations that we've presented. And all this is just for one simple element, a single phase of AC voltage and current. And the last thing is the power factor. And the power factor is just the ratio of P over S. In this case, look at the power factor. It is nearly 0, right? Cosine of 0 is essentially 0, right? So, okay, or sorry, cosine of 90 or plus or minus 90 is essentially 0, okay? Cosine of 0 is actually 1. And we can go back and check the resistor and see if that's the case right here. Cosine of 0 is 1, power factor is 1. This is like a resistor. Okay, so this tool will be uploaded to Brightspace so that you guys have access to it. If you're just watching on YouTube, it wouldn't be too hard to recreate, right? You could go here, have a column of time. You could punch in your formulas that are listed here. Okay, they're not too bad. You just would have to make sure everything is in the proper radians because that's what Excel likes. Okay, these last two columns that I've shown here are just the average. You can see it, the average of these instantaneous columns. And notice they should match P, the real power. And we can look here, in this case, P is 5 watts, right? And look, these are pretty close to 5 watts, 4.8. If I had increased the time and integrated, or sorry, averaged over a period, these would be bang on 5 watts, all right? Okay, I hope this was a good review and visualization tool showing the different properties and equations related to a single phase of AC power. Okay, have a great day.